We are today here for the tutorial by Professor Gianni Antichi. Let me very quickly introduce Gianni for those of you who might not know him. With a short bio, Gianni Antichi is an associate professor at the Dipartimento of Elettronica, Informazione e Bioingegneria of Politecnico di Milano in Italy, and is also a senior lecturer at the School of Electronic Engineering and Computer Science of Queen Mary University of London in the United Kingdom. His research interests sit at the intersections of networks and systems, and the goal is to develop hardware software co-designs to improve performance and efficiency of end-host applications, as well as packet processing programs. He received a PhD in information engineering from the University of Pisa in Italy, and his awards include the best paper at ACM SICOM in 2017, ACM SO-SR system in 2019, as part of the NET FPGA project, and the EPSRC New Investigator Award and the Facebook Networking System Research RFP in 2020. So, Gianni, the title of the talk is exactly in line with what we just said. Floor is yours.
Cool. Thank you, Massimo, for the introduction. Thank you for coming and for having me. Today, I want to talk a little bit about some years of suffering of some of the people I've been very lucky to collaborate with. But in the context of this talk, I want to talk a little bit about starting with the timeline a little bit. Now, 2007 is really, I think, an interesting date, because this is when the first NetFPGA boards became available. And actually, there was an email sent around where people at Stanford, they were suggesting that, that would have been available in less than a month for people to buy it. NetFPGA was an FPGA board with let's say, basic Ethernet connectivity. Now, after a year, I started my PhD back in Pisa, and at that time, the line rate was considered, let's say, 1 gigabit per second. Now, as let's say, a very young PhD student, I start approaching to the life of researching on FPGA and acceleration for packet processing, but then I got, backed into reviewers straight away complaining with my ideas, because the point was, why can't you need an FPGA board, right? So why you need hardware? Can you just buy a better CPU? Or can you, don't mess with the network equipments, or, can you just do it in software? Hardware is hard, but why you need software? And that was like more or less my reaction at that time. But then, slightly time changed, and with 2010, we had like line rates that slowly became 10 gigabit per second. But at the time, also at the time that where 10 gigabit per second became a commodity, there had been like also, or let's say, software APIs and I/O for improving software processing, like a kernel bypass for the masses, like cases like a NetMap, a DPDK, PF-Ring, and so forth. And then I got, at that time, I still proposing hardware acceleration. I was having like a sort of a feedback, like, can you just use NetMap? Or DPDK to the rescue, you don't need more hardware. Just go ahead with software. Why you need hardware? Now, hardware is hard. There was still always this sort of a complaint on hardware is hard. But then slowly, that was still me. And then slowly in 2015, 40 gigabit per second became commodity. 100 gigabit per second followed up. And then was when the first programmable NICs came up. And then suddenly there was a shift on reviewers, let's say, perspective, where I think the comment was, oh, yeah, this is a great idea. We really need an FPGA, or hardware is hard, it's true, but we have a high-level synthesis or high-level programming languages that you can compile into hardware. So suddenly, the idea of using hardware was right, really more compelling. And that was me, right? So me happy. And now we are here at today's. And if I try to think a little bit in perspective and I ask myself a question on what has changed, the problem is we can't longer expect a new general purpose processor to improve performance exponentially. And this is like a sort of a fairly stated and known Moore laws, and they're not scaling. And because of that, then people start thinking about how to get performance. And if we try to look into a sort of a very 10,000 feet view of what you can get from a system, which is, you have your application, you have some kernel space, you have then, a PCI Express where then you have a network interface card, and everything, this is your server connected to a switch. You start having this mechanism to offload part of the application logic into the network interface card, or even down to the switch with the programmable switch. And this allows basically to have less PCI Express transactions and reduce the amount of allocated SK buff, and basically release the pressure on the CPU. And there has been like a lot of work, right? So recently, really advocating for that. I'm not even start mentioning all of them. And this is like fostered by also the rising of new programming languages like P4. But at the same time, there is also this current trend of saying like, yes, that's not only hardware, so that allows us to get performance. We can even trying to push down application into the kernel space, because if you do that, you basically remove kernel to user space transition and reduce the amount of data returned by a syscall, and then basically you get improvement on the CPU utilization as well. And this is again, mechanism like eBPF and P4 allows you to do that. And there has been like, again, even in this case, quite a bit of research in trying to show how you can do that. Cloudflare has been like a recently pretty big advocate of that, but there are like a paper explaining how you can push programs in the NIC driver with XDP, or how you use a P4 as a language that then get compiled into BPF and then inside the Linux kernel. So there has been like a really a lot of interesting work in this area. But then, starting from this context, I would say, and also as the title of the talk suggests, performance is a king and is a kind of a mountain that we want to climb, right? So, and this is kind of me here, where, I am here with a double sword, which is a very pretty sort of a metal analogy. But, on the one side, what I think is a good to go is to try to get performance through new computing primitives, and on the others through better compilers. And that's what I'm going to try to advocate during this talk, which is potentially not the only two paths, but the path that we should take forward. And let me start with the first one, right? So I wanna take as a working example, like here a sort of a database application to advocate on what do I mean with new computing primitives. Now, let's assume we consider like a classic case of a telemetry system in a data center network. So here you can see on the right a sort of a classic representation of a data center network, where you have a sort of a fat tree topology, basically some switches, some racks, where you have some server installed in racks. And generally, what you have in a telemetry system, you have switches that they report data, And you have some collectors, so some specialized software that is installed in dedicated server that collect information from all the switches. Now, the thing is, data center, at least, a large scale data center can comprise even hundreds of thousands of switches. And this is something that has been reported by many companies. One of the latest one was Alibaba with this paper presented at ACMC-Com 2020. But the interesting part is that they were also arguing that even a single switch can report a few million telemetry reports per second per switch. So if you think about it, this becomes really a lot, because if you look at, for example, if you take like a sort of a stack of a software that needs to get all these reports, and so you need to invest a CPU cycle to process the packet, so the packet needs to arrive. Then you need to parse the packet to understand what type of report it is. And you need to insert these data in a sort of a data structure that you might want to or query afterwards. So basically, you might have like an increased need of number of cores just dedicated to the specific collection telemetry software. And the problem is the more reports to process, the more cores needed. And to the point that you might have to start investing full racks just to ingest the few million of telemetry reports per second. And this is just one phase of a problem, right? So if we look about at the other side, the more that you increase the network size, you will have more switches, and potentially, if you decide to gather all the telemetry for all the switches, you might end up in needing like an humongous amount of cores, and this becomes really expensive. So then we start asking ourselves, right? So why this is so expensive? Where is the problem? So we start by looking at profiling and a high performance collection stack, right? So we take this paper. This paper is an interesting paper from NSDI a few years ago. They were discussing about really how to optimize software for collecting telemetry data, which is really what we cared here. And this is one of the is an open source version of this software, and basically we try to understand where the time was spent. Now, as you can see here, running this profiler, we suddenly realize that a lot of time is spent really in inserting the data into the data structure. So basically, some time is spent in packet arrive, so the report arrive, you need to invest some CPU cycles for the I/O, so that the packet needs to reach the application. Then you need to invest some cycles to parse the packet, understand what type of report it is, and then insert in the data structure. Now, the first takeaway by looking at this figure is that the system is clearly here CPU bounded, meaning that you increase the number of cores, you increase your throughput or your ingestion throughput, which is good. But the most cycles are spent really in inserting data into the internal database. Now, this means that basically fancy I/O, let's say, stacks like DPDK, AFXDP that bypass the kernel do not help a lot here, because anyway, this is not the bottleneck. So then we start asking ourselves, can we leverage hardware to help a little bit on this? And our initial provocative question was, what if switches insert directly queryable telemetry data into collector memory, entirely bypassing the CPU? Because if you do that, then basically you remove this big bottleneck. Now, it turns out that there is a well-known protocol that is called RDMA, which RDMA stands for Remote Direct Memory Access, that allows to write the data in a memory bypassing the CPU. So then the question that we start asking ourselves is, if this is a collector, and a collector will have a network interface card because it needs to be connected to the network, it will have a CPU and some memory where you store your data structure. is there a way that from a switch, you trigger an RDMA request inside the collector and you just put the data into the memory? Because if you do that, then basically that's a win. So here's the problem. The problem is RDMA is limited to simple operation. So basically, with RDMA, if you want to use it in this way, and what I mean by that, without using CPU involvement, you can just do simple read or write or simple compare and swap, fetch and add sort of operation. So, and also RDMA requires also explicit addressing. What I mean by that is which needs to know exactly where in the memory it needs to write in the collectors. And this makes everything way more difficult now suddenly. Because I'm gonna try to explain to you why this is difficult with a thought example that reminds like a little bit here, like a lecture on the distributed system and concurrency, right? So let's assume we have here our data structure in the collector, which is a simple linked list, right? So where we want to append events that they happen alongside that they happen. So at time 0, or I have event A, then B, and then I want to append events, another event here at time 2. Now, if, how can we have all the switches here in the network? I represent the 3, but there might be more that needs to write in this data structure. But the question is, how can we assure coherency here? So what you can do, you can try to do some form of a switch coordination. So the switch talk each other and then decide when to write. But of course, this imposes too much overhead. And the reason why it imposes too much overhead is because a switch needs to report the telemetry data, cannot wait on trying to agree who's the switch in charge of writing into the collector. So we really didn't want to go down this route. Of course, it would have been possible, but we didn't want to go down this route. Another things you can do is, again, this is from Software Programming for Distributed System 101. You can have a sort of a semaphore, like a lock in your collector, and you can have a switch that, take a lock, then writes in the data structure, then release a lock. But again, this will require an additional RTT where the switch needs to write into the data structure, needs to acquire the lock, then I can write, then it needs to release the lock. And again, this was against our idea of, we wish really to have something that, we don't want to wait for anything, because again, telemetry is about the switches accumulate data and just send it. The other problem was, anyway, it was not just about acquiring the lock, but it was also, if you remember what I said at the beginning, for RDMA, you need explicit addressing. So this would have mean, if you want to go down this route, would have mean like acquiring the lock, then reading what's the last, your tail pointer, and then writing, and then updating the tail pointer, and then releasing the lock, which is like completely insane in my mind if you want to do something high performance, because again, switches in the meantime, they want to report and you have many switches. So then at that point, we face like a sort of a roadblock. We say like, okay, what shall we do? So we take a step back for a second and we try to understand, okay, let's try to see what are really here our wish list. The wish list is to have definitely something that impose low overheads as switches, because at the end of the day, the switches, they're not supposed to do fancy things. And the switches, they're not supposed to be switches, right? So just forward the data, accumulate data for telemetry, but you don't want to have a very heavy protocol. So we need a lightweight protocol. But also, we don't want to rely on collector CPU because that's where we started, right? So because the CPU is the bottleneck. So we want to have a lightweight protocol, but it has to be a sort of an RDMA-like protocol. We want to have a coordination-free updates. What I mean by that is we want switches just to push telemetry as soon as they can without even waiting for each other agreeing or having locks on the data structure. And finally, we want to preserve the data organization. So basically, we want the switches to write data in a way that is then easily queryable afterwards, right? So it needs to be directly organized in a queryable manner, because this is a telemetry system. You want to, or being able to then poke the telemetry system and understand what's going on. So basically, we want a sort of a memory layout aware RDMA verbs. And I'm going to try to give you an insight with what we came up with. This is something that we presented at SICOM a couple of years ago. And the idea was, let's assume here we have our collector. So it's a software running on a server. Definitely this collector will have a last hope switch. So a switch directly connected to a collector. Let's assume this is a programmable switch. And the connection between this programmable switch and this collector is just RDMA protocol. If you have that, basically you free the CPU. And then you have all the other switches in a network that they talk with the last hope switch, and they will have to talk regardless, even if you don't use our solution, because at some point the collector needs a point to connect to the network, that they use our protocol that we call direct telemetry access. Now, we created quite a bit, and the idea is to have a collector where we have write-only data structures, that the switches report the data using our custom protocol. So the memory layout RDMA verbs that I was discussing before. And this sort of a last hop switch is slightly different because it translates the standard RDMA calls and provides explicit addressing. So basically translate from our fancy protocol DTA to a classic RDMA and provide for explicit addressing. Now, from a very high level perspective, you have then a switch that wants to report S. It writes it in a packet with our own custom header, arrives at the last hop. Or this switch understands our custom header and say, oh, this means that I need to read or write in this memory at the collector at address A, for example. That's a very, very high level idea to give you a sort of an insight on how it works. And I'm going to provide you an example, right? So we have a different memory layout verbs, and I'm going to give an example just for a key value store. But in the paper, we have more examples. For this talk, I just want to give you an insight on what we were thinking. So for a key value store, the idea is really you want to have a stateless mapping between a memory and telemetry key, right? So basically, a key value store, think about it is the case where switches report flows and the number of packets seen for that flows, right? So this is like a sort of that you can consider this as a classic key value store. A key is a flow, and the value is the number of packets or bytes that specific switch has seen, right? So, and the idea is that the switch then, they use our primitive called RDMA key write. They send this to the last hop switch, and the last hop switch basically convert this call RDMA key write into an RDMA write. And I'm going to give you why this makes sense, right? So, and I'm going to take an example where a switch report the flow sizes, for example. So the key is the flow ID and the value is the count. So this is the memory on the collector. Our protocol just sends a count, and basically what we are going to write in the collector memory is randomly a 3 hash function that they are different and independent, the same count, right? So the hash function is hashed with the flow ID. So you basically are going to write into randomly in the collector memory in 3 places. You have a data redundancy, of course, but then you might have another flows that comes into the game and writes another 3 times randomly. I'm saying 3, but we have a trade-off between a space and collision, and we have this analysis in the paper. I don't want to really enter too much into this for a second. But anyway, the takeaway is basically you can, by doing that, in a random way, you're writing into the collector's memory. But you can encounter also the write, like as in this case, you can see like before this part of the memory was written by the orange one, and then suddenly by the green. So the question is, how do I read the memory now, right? So you need to know the flow ID, because if you know the flow ID, you know the hash, because the hash is something that you set it up, and then you can query and you can see the value. The problem is, how can you know if a memory was not overwritten, like in this specific case? The idea was that we decide to add this basically a simple CRC with a key. So this way, we can always backtrack if there was a collision. And if I backtrack that there was a collision, then I just check in another memory space that was supposed to be hit by my key. So we create several primitives for key value store, for a sort of a fancier key value store, for appending list of events, for merging sketches and so forth, for another variation of key value store. But the idea was really how cool it would be if we have a system that is completely independent by the specific monitoring element that is run into the switch. So basically, we wanted to show that by using these different primitives, you could support different telemetry events, the different telemetry systems that they have been implemented in switches. And then if you use that, basically, you can basically readapt your system. It's like, in some sense, it's like creating a socket API for your application. And here, what we create is a sort of a socket for your telemetry data. Now, does it work? Yes, otherwise I wouldn't be like probably here presenting, but here in what we show is the amount of throughput, so how much data we could ingest into the memory for our system, varying some primitives and comparing with the standard solution like the multilog, which is the first one that I started with profiling, INT collector, a BTRDB, that they are open source system. This depends, let's say the performance of our writing depends a lot on the type of primitive that we use, simply because different primitives, they have some different trade-offs, and because of that, they might have someone can be a little bit lighter, some other not, but we definitely have a pretty good performance. And actually was even when implemented this DTA protocol on our switches, it was a pretty lightweight. If you compare, like for example, an implementation of a fully RDMA from the switch, this would be like pretty heavy in terms of resource utilization on a programmable switch. But our protocol basically is as lightweight as a UDP, which is kind of great. Now, the question is, I wanna then ask myself is, it seems like hardware is a nice way to go here, but do we need really to give up with software? And that's where really brings me to the second part of the things, where I don't believe we really need to give up on software and just embrace hardware, although I have a lot of background on hardware, so I really like hardware. But I want to take as an example here to advocate of we should build better compilers. I wanna start as an example of packet processing programs, right? So if you think about how software compilation is done, is basically what you have is you have some programs in P4, eBPF, or DPDK, that they use DPDK. So they have their own program semantic. You give into or an input into a compiler and optimizer, and this creates a sort of a data path with some tables. That's more or less a very high level view of what is happening in software compilation. Now, what if we can do something like that? At runtime, we can provide back code behavior plus workload information, and at runtime generate a new shiny code. What if we can do that? How cool it would be? I'm gonna try to demonstrate why this makes sense in the context of a packet processing program. So the first things I want you to notice is when you compile a program, especially for packet processing, network configuration is unknown at compile time, right? So you compile a program, you don't know, or if your network use VLAN, VXLAN, MPLS, or whatever. And those are all branches that they are present in your program, right? So what we try to do here to try to understand the benefits of trying to specialize the code based on configuration, what we took a Catran. A Catran is a load balancer from Meta that is, according to Meta, they run in production, and Meta is a layer 4 load balancer, basically. But it's a layer 4 that can be used also as a layer 7, like HTTP type of load balancer. So the things we thought, like, let's assume that Catran inside the code is, has a lot of branches because it's able to manage UDP code, weak code, TCP code. Now let's assume we try by hand just removing all the branches in about the UDP because we wanted to use a Catran as a HTTP2 load balancer. So basically remove all the processing are related to TCP. Suddenly we realized that the Catran was running 12.2% faster. And the reason why it was running 12.2% faster is because if you remove branches, you make it easier for the branch predictor of the CPU to basically to predict the right branch, and so going faster. So the takeaway really number one is that if you want to specialize networking code for slowly changing input, like network configuration, improve performance. But this is not the end of it, right? So let's try to go beyond the idea of specialization for stable configuration, like the one that I discussed before. And let's assume we could somehow potentially do optimization at the packet level. What I mean by that, let's assume you realize you have, think about it, you have a sort of a switch. And you realize that you have a flow that is get hit many times. You have an entry that gets hit many times. So if you think about it, if you have a switch and you have a table, your performance is always bounded by the fact that for every packet you need to do a memory access on that table. But if you realize that you have a very much hit entry, then potentially if you could recompile your code, and inside your code you're saying, hey, if this is the entry, just do that, otherwise you're checking the table, then basically it's like inlining into the code the exact entry. Then suddenly we realize we could gain performance. So this is what we call it, sort of fast path. Now, of course, this works in the presence of skewed traffic, right? So because you need to have a entry that is hit many times. But then we found interesting this thing. Now, when we realized this, we tried to think about a step back, right? So because the takeaway was clear that for maximum performance, you want to specialize with respect to inbound traffic patterns. But then, the question is, but this is not new, right? So dynamic compilation of software is not really new, right? So there are like tools like that they are called POGO type of tools that they exist. And the idea of those tools is to use the result of profiling to optimize code, which is exactly what we were doing right now. So then the question we ask ourselves, okay, so if those exist, can we just use those for packet processing programs? So we took two optimizer, one from Google that is called AutoFDIO, and one from Meta, Facebook, that is called Bolt, and we try to apply these in our scenarios. And originally, I thought we would have get like the improve of performance that I was showing you before, right? So I was expecting at least 20% or something like that, but suddenly, and it was pretty unfortunate, we saw like, okay, so we don't have like really lot of, so they improve. You can see like here in the red, when you apply the POGO tool to those, to our starting program, we could have a plus of 4%, but it was not exciting as before. So then the question is why? And the reason why we realize is because those are tools generated for normal application, not packet processing application. So they look at the cache misses into the CPU, but packet processing programs, they are really influenced by domain-specific knowledge, like traffic profile, like the content of the table of your data plane. So we need to be a little bit more domain specific. And that triggers us to build what we call the Morpheus And this is something that we presented at ASPLOS a few years ago again. And the idea of Morpheus is really to create an optimizer for BPF code that basically can take as an input the LLVM of the code, just perform some analysis, it instrument the code, so it just put some, let's say, probe inside the code, and then based on the results of the instrumentation, optimize a runtime the code and give it back, and then continue this in a feedback loop. Now, this is going to be too long to explain all the steps and potentially even not very useful. What I want to focus is just a tiny bit on the optimization, because I think this is really the interesting part. We built many different type of optimization, and the idea, again, as I said before, is to use the result of the instrumentation to drive the optimization here. Now, the type of optimization that we have done, some of them, they were dependent on the input traffic, so on the type of traffic that you get. Some other, they were dependent on the not on the input traffic, but only on what I defined before, stable configuration, on configuration. Like, for example, an optimization of removing tables where there is no entry. What I mean by that is, let's assume you write a software code where where you basically you expect to process IPv6 or IPv4 traffic. So then you compile this in just in a binary, and then you run it on your CPU, but then you don't insert any rules related to IPv6. Now, in a normal scenario, you will have always the, let's say, the lookup in the table. They will report nothing, but you will have a lookup in the table. But if you realize that, you can remove the table in advance. So this is something that is not dependent on the input traffic, but more on a configuration. Now, I'm not gonna talk and bore you on with talking about all the optimization. I just want to focus on two types of optimization that I found probably a little bit more interesting to look. The first one is dead code elimination. And dead code elimination is about really removing branches that are not being used. Now, if you are a little bit familiar with compilers, that code elimination is not a new thing. That code elimination is used by many compilers. But here in this context with Morpheus, we give a slightly different spin. And to explain you how it works, I'm going to show you an example, right? So look at, for example, at this code here on the right. This is a sort of a representation of what really the Catran, the L4 load balancer from Meta does, right? So you have an input packet, you parse L3, parse L4, then it tries to get the virtual IP, the port, and the info, and then it does something. If you see that there are like the packet is a quick, and there are like some quick as a virtual IP. Now let's assume that. So what is that? What here our tool will do at runtime is static code analysis will find the fact that there is a lookup in a virtual IP map, which is basically a table. Then in Morpheus, what you will find that in this table, there is nothing configured for quick. So if it finds that there is nothing configured for quick, I just return back here, it will just rewrite the code, the source code of Catran, just changing instead of this, just putting 0. Now, if you put 0, then when you run this compilation, the standard compilation, then the classic dead code elimination will be triggered. Will be triggered because the classic compiler will see here there is a 0, this branch will never happen. So the classic LLVM dead code elimination will remove the dead code for us. The smart here bit is about realizing that this was 0 by looking at the table, and that's what something we enforced. So this is an example. I'm going to give you the other example, which again, it brings back to one of the first use cases that I bring, which is the just-in-time compilation. So inlining frequently hit the table into entries into the code. Now, again, here I'm going to take as an example, again, a part of a code of Catran. And here, if you look about this code, what you do is basically, yeah, a packet enter. You check the a connection table, and based on this result, you assign a backend or you update the connection table. This is a load balancer, so it kind of makes sense if you look at that, right? So, and let's assume we are in the presence of skewed traffic. So let's assume that we have a few flows that account for most of the traffic. Now, the code analysis here, what we will do, we'll discover the fact that there are like, what are the relevant fields for this connection table lookup. And the instrumentation that we have, so our probes installed inside the code, will realize that there are like some entries that are more hit than others. So basically, we will rewrite straight away the code by saying like, if packet is this 5 tuple, just go to backend 15. Because we know already this is, this is the things that you should be doing. Don't just check the table. If instead, if it is these other 5 tuple, just go to this. Otherwise, just look at the table. So basically, it's like sort of a just-in-time compiling the entries into the code. Does this work? Yes, it actually turns out that it was very nice the way that we work, right? So we compared the behavior of running our compiler against a different type of code, a switch, a router, catran, BPF, IP table, so all BPF code. And we try to generate traffic with different type of locality. And of course, if you have a lot of locality, more optimization can kick in. And then, of course, you have a better average throughput. If you have no locality, then you are in kind of worst case scenario. You still have some optimization, so you have still some leverage. You can get a little bit better. But of course, you will not be able to go as good as when you have a high locality. Why this is the case, right? So looking at the microarchitectural level is more or less the things that I was mentioning before. Here, basically, what we're trying to check is the number of cycle, instruction, branches, and load misses that we have. So basically, when a traffic level optimization kicks in, what we have is here is the decrease in number of instruction branches and load misses. So the higher, the better, because you have a decrease of those. And of course, you can see like you have a decrease of a lot of last layer cache load misses because you have less a decrease of branches. If you have a decrease of branches, you make it easier for your CPU, let's say, branch predictor to basically do the right job. And if you have, otherwise, of course, if you have, let's say, non-skewed traffic, you will not be able to do this as before. Now, the lesson that I learned by working on these two projects, there are like multiple lessons that I really want to share, and I hope this can be also used for having some discussion. So the lesson I learned is really scaling application performance is possible. And now the interesting bit that we do have now is we have a fully programmable stack. We have switches that they are programmable, NICs that are programmable. It's easy to inject code into the kernel. But the thing is that I realize is very hard to pick what functionality to offload. So the reason is because if you think about as a programmer and you have your application, what you have to do, you need to understand application and offload capabilities. So you need to be able to understand what the application does, but also what are the capabilities of the kernel or the NIC or the switch. But also you need to reason, when you think about that, you need to reason about the improvements from the offloading. You need to implement a separate component, so you need to implement the part in the kernel, the part in the NIC, and so forth. But also you can miss opportunities because you can test only so many options, right? So you are like just a single person. And that's why I think, yes, scaling application performance is possible, but we need smarter, not just better compiler. I think we need smarter compiler. We tried to do a first step into this direction with an AutoS paper that we presented last year, now 2 years. where the idea was really, if we get the application here and we do some analysis, selection, and generation, can we do based on some cost table or decide automatically how to split code between kernel, NIC, and switch? We were trying to argue ourselves that was a workshop paper, so we didn't have a complete solution, but our idea is really, can we automatically infer what's the best separation here? So that's an open question, I think, right? So that's something that I would like to continue working, but it's a sort of an open question. And changing for a tiny bit of topic, but again, going into the same direction, I do believe the scaling application performance is possible, but you don't need just smarter compilers. You need also vertical co-design at this point. So vertical co-design between layer 2 and layer 7. What I mean by that, you need to be, you might be in cases where the hardware offload might need to full stack processing. Now, I'm going to give you an example of what I mean by that, right? So let's assume we are here in a case where you have your NIC, the NIC has a queue, and this goes to a software proxy, and then the software proxy redirects the traffic either to application 1 or application 2. And this is a sort of pretty common things to do in a data center right now, right? So this provides a single interface for rapidly changing settings, for load distribution and security. And there is like an interesting paper from Meta that describes their solution. For example, they call it service router. Now, and I'm going to give you an example here on something that it can be even more simple than a service router. Let's assume you want to dispatch incoming HTTP request based on the prefix of the path field in the HTTP header. Example why you want to do that is a very silly example, but just to give you an insight, you have a course enrollment service that's comprised of multiple independent processes on a server, and this server manages all the courses from all the departments across the different campuses. So you have basically a process for CS, a process for EE, for example, and you want your service router, your L7 dispatch to dispatch to either the process that does a CS or EE, but this depends on the path fields in the HTTP header. Now, we try to understand really, because this is possible to be done now, right? So you take Envoy and you can do that. Now, we try to understand really what's the cost of doing that. So we took like an HTTP load generator, WRK, we took Envoy, and we took a fast HTTP as a final application here. Now, what we realized that the per request latency here without Envoy and with Envoy, basically we realized that the latency increased a lot with Envoy. Now, it's not surprising that increase a lot because if you put something more, you would expect that the latency will be bigger. But what was interesting to me is that basically 60% of this added was mostly due to L7 policies on extracted data. So basically it was for Envoy to parse the L7 packet and apply the policies and understand where to redirect the packet. So that was, and 35% is inter-process communication, which kind of makes sense because Envoy will run on a core, you will have your final application on a different core, so you need to move data between cores, and that costs a little bit. But to me, the interesting was the 60%. But this is not just like that. It's not just about latency. When comparing the throughput, we realized that by just adding this layer 7 functionality, it would have put you in a situation where your throughput that your, let's say, this fast HTTP with WRK can sustain is 9x lower. Again, is the cost of having Envoy. And you might say like, okay, so, but if you want Envoy, you need to be ready to, or let's say, and happy to kind of pay this cost. Now, we ask ourselves, like, can we do better here, right? So can we do better? And what I'm talking about, can we do better, means to me is in a world where a NIC just sent to a software proxy and then you go to an app, is there a way that you can tightly couple the queues that they are inside the NIC to specific caps? And this is like a little bit harder if you think about it. It's harder because this sort of things is possible now in a form of layer 3 and layer 4. You can couple based on ports to up. But if you have, if you want to redirect based on layer 7, you cannot do right now on normal NICs. And the reason why normal NICs do not support that, apart from like it's challenging, but it's because if you think about it, an L request can be segmented into multiple packets. An HTTP request can span multiple packets. And this becomes way harder now to check into the hardware. And, you know, but also it's not just about that, right? So many applications use variable length fields. So you will need the hardware to try to extract fields at arbitrary offsets as L7 request payloads vary. Now, but this is an example of what I mean by we need a co-design application transport the hardware, because if you decide that this is a good idea and we have some sort of ideas on how to implement this is like right now is a little bit unlucky paper that is an ArchiveX. It got rejected a couple of times, but at some point it will find its home. The idea is if you are convinced that this is a good idea to do that, then you need to be ready to or manage the transport in a NIC. But if you manage the transport in a NIC because you want to reconstruct the packets, the segments, then you need to be able to start thinking about the vertical co-design from layer 2, layer 7. But also, what I want to continue is scaling application performance is possible, as I think I said millions of times right now, but I strongly believe that we need a better platform to understand how to do that. So recently, we started working quite heavily on a project that is called OpenNIC, which is a project from AMD Xilinx that provides you a code base for, let's say, an open source network interface card. And of course, if you start from that, you can write your offload, you can write your application in Verilog on VHDL, which is very exciting to me, but less exciting for other people. So right now we have people in our group working on trying to provide abstraction for injecting P4 programs with, let's say, overlay inside the FPGA. So basically gives you abstraction where you can just code your P4 and this will be injected straight away dynamically into the NIC, into the FPGA without recompiling the FPGA. Thanks to Francesco to that. But also on a separate side, we had Simone that tried to use a compiler called Nanotube provided by Xilinx to try to see if you can, at runtime, take an eBPF code and inject that into the FPGA. And, and this is like a very hardware-ish. If you are more into the software, lately we had also Marco that basically improved the behavior of the driver of OpenNIC to be able, so you can dynamically inject eBPF code into the driver or use AFXDP, which is a new, let's say, socket from Linux that allows you to pass packets from the driver directly to the user space. So then this is what I mean, like we have a full stack programmability with eBPF and MP4, and where I think now is the time to have fun. And I strongly believe that this will help a lot, the community on its own. And finally, I think, yes, scaling application performance is possible, but I think the most important thing is that we need really more integration between different communities, mostly from programming language, system and networking, and computer architecture. And with that, I want to conclude the talk by giving special thanks to all the people that they, in a form or the other, they contributed to the presentation that I gave. but also the cat that today was not possible. She was not available to deliver the talk, so that's why I came here. A lot of cables, and I'm happy to take questions.
Thanks a lot, Gianni.